Alright, we are going to be looking at the PowerPoint called The Atmosphere. It's chapter 16, and it covers the following topics. So we're going to talk about the difference between weather and climate. We're going to look at the composition of the atmosphere. We'll take a look at the importance of ozone, because that's an important part of the atmosphere that's often overlooked. We'll take a look at the vertical structure of the atmosphere, and if there's time, we'll look at pressure, reflection, transmission, and absorption. We'll look at albedo, and finally we'll take a look at the greenhouse effect, and that plays an important part in terms of climate change today. So looking at weather versus climate, this is a topic that we need to talk about right away. So when I use the terms weather or climate, you know what I'm talking about. Weather is constantly changing. Weather is the day-to-day occurrence that you see outside. It's hour to hour, it's day to day. It's the weather report that you get from like Vince Candela when you watch the news. Basically, it's the state of the atmosphere at any given time and place. So, I don't know, if you look in Germany today at 5 o'clock, you can find the weather. You can figure out the weather. It's the, again, state of the atmosphere at a given time or place. And it changes continuously. It can kind of seem erratic at times, but you can, over time, come up with generalizations of weather variations. So you're able to generalize weather variations that we see, so it's not completely erratic. You can think of climate as a description of the aggregate of weather conditions. So if you take all the weather conditions and kind of bring them together and add them up, we get climate. It's based on observations that have been accumulated for many years, so it's not just a small amount of data. Climate data is data that has been continuous and ongoing. Don't think of it as average weather, though. Don't think of it as like the average that you get from weather conditions. It includes extreme variations as well as also included. A great way you can think of it is that climate data cannot predict weather. Okay, so climate data cannot tell you the weather, what the weather's going to be like on a specific day. For an example, it could be cold, it could be warm, it could be raining. Climate cannot tell you this. Climate can tell you almost basically trends. So a great way to say that I quoted from the textbook is climate is what you expect, but weather is what you get. Okay, so think of climate as aggregate of weather conditions over long term. Okay, weather and climate both are expressed in terms of some basic elements. These include temperature, so the amount of the temperature. So whenever you get a weather report, or even when you talk about climate, it usually discusses the air temperature. Humidity is a good one. So we'll talk about this, I think in this PowerPoint or later on, when we'll talk about dew point and percent humidity. The amount and type of cloudiness is also included in weather and climate. The type and amount of precipitation. So is it going to be sleet, snow, rain, and how much? Air pressure. High or low air pressure. This is important. This is the big L or the big H that you see on a weather forecast map. And speed and direction is kind of cut off here, but speed and direction of the wind. Wind is a big one, so make sure you fill that in on your PowerPoint, your notes sheet. Speed and direction of wind. So all of these are basic elements of weather and climate data. Looking at the composition of the atmosphere, okay, you notice what? You notice that it's mostly nitrogen. So about 78% is nitrogen, only 20% is, or 21% is oxygen. So when you take a deep breath, 3/4 of it is nitrogen, about 1/5 of it is oxygen. And then we have some trace others. So we have a little bit of carbon dioxide, some argon, and then some trace elements of others. So again, most of it's nitrogen. Nitrogen is what makes the sky blue. When the sun hits, photons interact with the nitrogen in the atmosphere, it gets scattered and creates this blue effect. So that's what you see when you look up at a blue sky. Let's talk about ozone. Ozone is just it's just a molecule. It's a molecule composed up of 3 oxygen atoms. The oxygen that we breathe is composed of 2 oxygen atoms, O2. So ozone is O3. There's very little ozone in the atmosphere. It's not that much. It's very high in the stratosphere. So once we talk about the vertical structure, the stratosphere is an upper region of it. So here we go right here. Here's the stratosphere. It's pretty high up there. It's not the highest part of the atmosphere, but you can see it's pretty up there. The stratosphere, okay, it's up to maybe around 30 miles in height, between maybe 8 to 30 miles in height. Here's the stratosphere. You can see this layer right here where it says maximum ozone. Yeah, there, ozone. This is where the ozone layer resides vertically. It's essential to life on Earth, and here's why. Because ozone happens to absorb harmful UV radiation from the sun. So it absorbs the bad part of the ultraviolet radiation from the sun. So without the ozone layer there, this harmful radiation would affect the well-being of life on Earth. So anything that reduces the amount of ozone could affect the well-being of life on Earth. And this is important because in the 60s and 70s, this is really big. They discovered that we humans were releasing chemicals into the atmosphere and destroying or react with the ozone layer and destroy the ozone layer. So over the past 60 years, ozone layer is in jeopardy through pollution. The ozone layer is as thick as a credit card, so it's pretty thin. So what we're releasing were what are called CFCs, and now there's another chemical called HCFC. CFC just stands for chlorofluorocarbon, so chlorine, fluorine, and carbon. Okay, and these react with ozone and basically destroys it. It reacts with it and creates a different chemical, but it eliminates this ozone layer. So some examples are refrigerators, air conditioners, air-conditioned automobiles, industrial coolers, things like that. Aerosols, things like spray cans, hairspray, spray paint. These things used to have CFCs in them. If you look at a bottle of hairspray now, you'll notice that it basically says no, or I think it does. It used to say no CFCs on it, or does not contain CFCs. So these aerosols were being put into the atmosphere in mass quantities and having an effect on the atmosphere, on the ozone layer. So here's a video. I don't know if you can see this. I hope you can see this, but it's just talking about CFCs and the ozone layer. You can see in the video that the amount of ozone has been decreasing with the amount of CFCs increasing. So there's a relationship here. This green line is CFCs, okay, and this right here, this pink line, is the amount of ozone in the environment. Let me go back to the PowerPoint here. And you can see this depletion over time. So here's what it looked like in 1979. And here's the ozone hole in 2009. So they saw this hole developing in ozone. We've decreased the amount of CFCs being released. The hole is starting to close up, but you can see it's still there. Okay, so humans affect the environment. Here's they'll look at it over time. So you can see the year here is going up by year. You can see the let me go back to this. You can see the hole develop over time. So 1977, blue colors mean low ozone. Okay, so you can see that there. So that's ozone. So basically, it's a layer that absorbs harmful ultraviolet, and we were releasing chemicals that would destroy it, and it's currently coming back. It's coming back because we were banning these harmful chemicals. Okay, let's look at the vertical structure now of the atmosphere. Pressure is a big thing. So you can think of pressure as just basically the weight of the air above you. If I look up, I can think of a column of air going all the way into space, and it's this basically air that's pushing down on me. That's what you can think of as pressure. At sea level, it's about 1,000 millibars. So sea level is kind of the standard pressure that we use. If you've ever been in chemistry, you use standard temperature and pressure, STP. That's the standard pressure at sea level. So it's usually 1,000 millibars. Bars are commonly used. However, it's not the SI unit. I just want to note that the SI unit is the Pascal, which is a huge unit. So I'm sorry, Pascal is a very small unit. So 1 bar is at 100,000 pascals. That's a little complicated. So pressure, there's actually like 3 or 4 different units that we use. So you can use atmospheres. So 1 atmosphere would be the amount of pressure at sea level. You can use PSI, or pounds per square inch. This is like what you use when you fill up your car tire or bike tire. We can also use millimeters of mercury, mmHg. Hg is the symbol for mercury, and you can talk about how much the mercury moves when you measure the pressure in the atmosphere. So let's look at the pressure. At sea level, the pressure equates to about 1 kilogram every square centimeter. So every square centimeter, I don't know, about like that. So if you think of a bunch of square centimeters are on you, you're feeling 1 kilogram of pressure pushing inward. That's the amount of pressure that we feel. That's the standard pressure. Ends up being about 15 pounds per square inch. So per square inch, I don't know. Kind of hard to see with my fingers. I don't have anything. Maybe the face on my watch. Okay, that's feeling 15 pounds of pressure pushing in on it. That's kind of a lot if you think about it. Okay, so again, this diagram just shows this column of air being pulled down from gravity with about 15 pounds for every square inch. Pressure decreases at higher altitudes. Why would you think that would be? Well, if you think about it, if you're at a higher altitude and you look up, you have less air getting pulled down on you from gravity. So you have less air getting pulled down, which means the pressure decreases. So that, Denver Mile High Stadium, they have less pressure than we do here. Thinner air. If you've ever been, thinner air means lower pressure. And as you can see, the higher up you go, the air thins out. Okay, as the air thins out, you get less pressure. And less pressure means, if you're climbing a mountain or something, it's harder to breathe. Okay, so pressure, you should know, overall, generally decreases with height. Okay, so you can see if you have altitude here, here's pressure, and pressure decreases with height. Notice it's not linear. Not a linear change, but it changes with height. And it gradually gets to 0, and 0 pressure means basically you're in space. Okay, so 50% is to note as well, 50% of all the atmosphere lies below this line right here. So half of all of the atmosphere, half of all the air is right here. Okay, I'm probably going to end with this. I only got 2 minutes left in here. So let's talk about the vertical structure of the atmosphere. We have 1, 2, 3, 4 parts. 4 parts of the atmosphere, and it's separated, okay, with what are called pauses. So let's start with the troposphere. That's the layer that we live in. So if you increase in height, if you increase altitude, temperature will decrease in the troposphere. Okay, so here's temperature here on the bottom, height's on the y-axis. The temperature decreases as we go up in the troposphere. The rate at which it decreases is about 6.5 degrees Celsius every kilometer you move up. So if you move up 2 kilometers, temperature decreases by about 13 degrees Celsius. This is called the environmental lapse rate. You can see this if you ever go out to Colorado or look at some mountains. You can see where this kind of like the snow starts, and that's you can tell that with the environmental lapse rate, that's where this temperature crosses freezing point. You can kind of see like snow-capped mountains. Where that snow starts, that's with the environmental lapse rate. As you move up, temperature decreases. That's where you cross freezing point. The upper layer is called the tropopause. Okay, and speaking of tropopause, we will pause right here, and we will continue talking about the vertical structure of the atmosphere in class. So again, these videos are here for you to watch again. Probably a good thing to watch these maybe before the test. I'll try to get more of these out, but in terms of time, we don't have that much time all the way up to the finals here. So Thank you for watching and have a good day.